Hi everyone. Am I audible? Is the audio okay? Let me know if the volume is okay. Now is it okay? Volume? Now volume is okay? Okay, let's start. So today there is a small change in the schedule. Today this class we will take till 7:30. Okay, so from almost at 6:10 I have started, so from 6:10 to 7:30 we will take this class, and then from 7:30 to 9 there will be operating system class. So this is a change in schedule for today, only for today, and for other days, for all other days the schedule will remain the same. Okay, only for today this change is happening, so just make sure that you know this. Okay, so you can let your friends also, if anyone is missing this class, then you can let them know that the operating system class will be from 7:30 to 9. Okay, and this class will be from 6:10 to 7:30. From tomorrow onwards all the classes will be as per the schedule. Okay, let's start without any delay. Let's start today's lecture. So far we have seen many special type of relations, I told you, and now so we have seen reflexive relation, symmetric relation, anti-symmetric relation, transitive relation. All these relations we have seen. There is one last relation we can see, that is irreflexive relation. Irreflexive, this is basically completely opposite of reflexive, completely opposite. Irreflexive, what irreflexive says, you see, reflexive says that everyone should have a reflection. Okay, this is reflexive relation, means A should be related to A for all elements. Okay, for all elements this should happen, that A should relate to A. This happens in reflexive relation. Okay, but in irreflexive means completely opposite of reflexive. What it says that no one should have reflection. No one should have reflection. No one should have reflection. Okay, no one should have reflection. So what it means, if A is there, then A should not be related to A. For every A means no one should have reflection, basically for every A. So this is, I told you, this is not a horror movie. If you are standing, then you will see your reflection. Okay, but this irreflexive is like the biggest horror movie. If anyone is standing, then he can't see, like it's the world of ghost. Okay, so anyway, this is irreflexive relation, means no one should be related to themselves. No element should be related to itself. No element. Okay, so let's take one example. So you can take this example, that let's assume we have a base set. The base set is, I told you what is a base set. Base set means a set on which we are defining a relation. Let's assume our base set is n, set of natural number. What is set of natural number? 1, 2, 3 and so on. This is our set of natural number. Now we are defining a relation R on n. We are defining a relation R on n. You know what this line means, R on n. What it means? It means R is a relation from set of natural number to set of natural number. We have seen this in last class. Okay, Now we are defining this relation. How do we relate to elements? How do we relate to numbers? So A is related to B if and only if A is less than B. This is our relation. This is the rule. You can say either you can say this is the relation, or you can say this is the rule. Basically this rule will relate to elements. Okay, this rule. A is related to B. A is related to B if and only if A is less than B. Now tell me, the first question we can ask. Okay, let me just revise your concepts. Is it reflexive? First question, is it reflexive? This is my first question. Let's revise your concepts. Is it reflexive? Tell me. So you can see, you can try, but let me answer. Yes, this is not reflexive. This is not reflexive. Why? This is not reflexive because you can see, for example, you can take 3. You can take 3. Now 3 is not related to 3. 3, you can say 3 is not related to 3. Why? Because 3 is not less than 3. You can say 3 is not less than 3. So we can say that 3 is not related to 3. So hence this is not reflexive. Okay, this relation is not reflexive. Now let me ask you the second question. Is it irreflexive? Irreflexive. Irreflexive. Tell me, is it irreflexive? No, Nidhi, you have not missed anything. We have just taken one example, one relation we have taken, and I was just asking whether that relation is reflexive. Today we are looking at a new type of relation, that is irreflexive. Irreflexive relation says that no element should be related to itself. No element. Okay, no element should be related to itself. It's like extreme opposite of reflexive. Reflexive says that every element should be related to itself, and irreflexive says that no element should be related to itself. So these are extreme opposite of each other. Now you can check, you can try. This is irreflexive. Why? Because you can see that no element is related to itself. No element, whatever element you take, whatever, for example, whatever element x you take, whatever element x you take, whatever natural number you take, that natural number is not related to itself. Why? Because x is not less than x. That's why. Okay, so that's why you can see that no element is related to itself, and hence we can say that this is irreflexive. Okay, so this is the definition of irreflexive. So remember, these are two extreme opposites. Extreme opposite means on one side we have something called reflexive. This reflexive says that everyone, remember, everyone means every element, basically every element of our base set, every element of our base set basically should be related to itself, every element. Okay, and and irreflexive, what it says, irreflexive is extreme opposite. It says that no one, it says that no one, okay, no one, basically no element should be related to itself. No element should be related to itself. So these are complete opposite. Now let me ask you one last question. Take this one last question. Our domain is a set of natural number. This is our base set. We are defining a relation on n such that, and what is this relation? So this relation R is defined on n such that A is related to B if and only if A plus B is equal to 6. This is our question. Now tell me, the first question I am asking, is it reflexive? The first question I am asking, is it reflexive? Nidhi, irreflexive means completely, extremely opposite of reflexive. Reflexive says that all elements, every element should be related to itself. Irreflexive says that no element should be related to itself. No element should be related to itself. So these are two relations. Now you can try. This is not reflexive. Why? Because you can check. For example, 4 is not related to 4. You can see 4 is not related to 4. Why? Because 4 plus 4 is not equal to 6. So 4 is not related to 4. Remember, 3 is related to 3. You can check. 3 is related to 3. Why? Because 3 plus 3 is equal to 6. So 3 is related to 3, but 4 is not related to 4. So because 4 is not related to 4, what we can say? That this 4 has no image. I told you, reflexive relation means not a horror movie. So if 4 is standing in front of mirror, then he should see image, but 4 is not seeing any image. Okay, so this is a horror movie, you can see. Anyway, basically 4 is not related to 4. 3 is related to 3. Reflexive relation says that every element should have reflection. Every element should be related to itself. Now second question is it irreflexive? This is second question. Is it irreflexive? Try this. Yes, Prerna, 3 plus 3 is equal to 6. But that does not mean that it is reflexive relation. See, for example, if you have a horror movie, then in that movie, not every house is haunted. There is only one house that is haunted. Okay, and the neighbors are not haunted. So if this 3 is like a neighbor. So if he is standing in front of mirror, then he will see image. But this house is haunted, and this is the house of element 4. So this house is haunted. You can see 4 will not see any image. So remember, reflexive says that every element should see image. Every element should see reflection. Basically, every element should be related to itself. Okay. So even though 3 has a reflection, 4 does not have reflection. And because of this 4, because of this 5, you can see 5 also does not have reflection. 6 also does not have reflection. So because of 4, because of 5, because of all these things, we can say that this is not reflexive. Now what about irreflexive? So this is not irreflexive. Why? Because irreflexive is completely extreme opposite of reflexive. It says that no one should see image. No one should see image. But no one should see reflection. But 3 is seeing reflection, you can see. Irreflexive says that no one should have reflection, but 3 has reflection. 3 is related to 3. So that's why this relation is neither reflexive, this relation is nor irreflexive. Okay, so is this point clear? So this is what we mean by reflexive, irreflexive. Okay, it's not reflexive, also it's not irreflexive. Okay, let's move on. If anyone has still any doubt, then you can ask me in the comments. You can ask me, or you can ask me after this class also. Now we will see something called order relation, partial order relation. Now we will see something called partial order relation. These are basically called partial order relation, total order relation. We will see this topic. What is this partial order relation? I told you we were studying something called relations. In these relations we have seen many special type of relations: reflexive, symmetric, anti-symmetric, irreflexive, equivalence relation. Now we have 2 special type of relations remaining. So these 2 relations are remaining. 2 special type of relations are remaining. One is partial order relation. order relation. So this is remaining. Another that is remaining, that is function. This function is also a relation, remember, this is a special type of relation. Similarly, partial order relation, this is also a special type of relation. I told you in relations we have already seen many special type of relations. Now equivalence relation, for example, if you remember equivalence relation, that was also a special type of relation. Equivalence relation is a relation which is reflexive, symmetric and transitive. All these three properties must satisfy, then we will say that that relation is equivalence relation. We have already seen this. Now this special type of relation we will see something called partial order relation. Partial order relation. Now you can see in the name itself, there is something called order. Okay, for example, if I write like this 1 2 3 4, then there is a order. You can see this is increasing order. If I write like 10 9 8, then this is a decreasing order. You can see there is a order. Okay. If I randomly write anything to 10 1 5, okay, 15, basically this is unordered. Basically I am randomly writing anything, whatever is coming to my mind, I am writing that. So this is unordered, but this is ordered, where there is order, decreasing order, there is a order, increasing order. Okay, for example, as I told you in the Titanic movie we have three orders. Okay, three orders. You can see the Titanic movie is a nice partial order relation. Okay, so in the Titanic movie we have three order. You can see. So here the third class people. Okay, our hero is also here, the DiCaprio whatever, and here middle class people, and here the heroine. You can see that she is standing here. You can see there is a order here. Basically the order means if you go from like if you go in this height, then basically the money you can say the rich people, like, okay, from poor to people, so from poor to rich, so there is a order. So you can see order relation means there must be some type of ordering must be there. Let's see what is this order relation. For example, all these are order relation. Don't worry, right now I am just giving you some intuition. We are not looking at definition right now, so don't worry, we will see the definition. Okay, we will see the definition, and then we will see how this intuition, how this analogy relates to that definition. We will see this also, so don't worry. So but all these are order relation, all these. For example, x is larger than y, so there is a order, like x is larger than y, so there is a order. You can see there is a order. Basically you are order, or you can say that basically this x is larger means x is bigger, means x is larger than y. So like this, like the status is increasing, like maybe y is poor, x is rich, x is larger, maybe so x is Amazon and y is Flipkart, so Amazon is larger than Flipkart. Anyway, so basically there is a ranking, or you can say there is a ranking system, like it's the rank 1, it's the rank 2, so there is a ranking, or there is something called order. For example, x is tastier than y, x is tastier than y, so y is less tastier, x is more tastier. Okay, so that's why, like this, maybe this x might be the maybe pizza, this y may be the tinde ki sabzi. So anyway, so you can see x has more rank than in the terms of taste. In the terms of taste, you can see the taste is increasing like this. Okay, x is faster than y. Okay, so then again you can order. For example, maybe this x may be the Usain Bolt, or maybe PT Usha. So this is how you can order. For example, x is a subset of y, then also you can order them. How can you order them? This is how you can order them. Basically this is how you can order them. X divides y, again you can order them. X divides y, x basically x divides y. X is part of y, again x is part of y means basically x is subset of y. So you can see all these relations. If you see then these are order relation. Now you will ask me, if all these relations are order relation, then what is a relation which is not order relation? So consider this, x plus y is equal to 10. x plus y is equal to 10. This is not a order relation. Why? Because you cannot put any order. For example, see, for example 5, you can see, for example 3 plus 7 is equal to 10. You can see 3 plus 7 is equal to 10, but 7 plus 3 is also equal to 10. So you can't say that this 3 the order the order is increasing here. No. Why? Because 7 is also 7 plus 3 is also 10. 3 plus 7 is also 10. Okay, so basically there is no ranking here. Basically both are same. You can see there is no ranking here. Okay, are you getting my point? See, if I define this relation x plus y equal to 10, if I define this relation, then this relation is not order relation, because you can see this 3 comma 7, this 3 comma 7, they do not have any ordering. Okay, 3 also relates to 7 and 7 also relates to 3. Sorry. So you can see there is no ordering here. But if I define this relation, let's assume I define this relation x less than y. If I define this relation, now there is ordering. For example, in the ordering 3 will come here and 7 will come here, 10 will come here, and so on. There is a ordering here. Okay, when I define this relation. So this relation is order relation. This relation is not order relation. Okay, are you getting my point? So don't worry if you did not get it. I am just saying that this is the intuition. This is the intuition behind order relation. Basically, in order relation, we can put the elements in some order. Okay. So basically in order relation, what we can do, basically we can give ranks to the elements. Okay, we can give some ranks to the elements, like in the Titanic movie. Okay, maybe this is rank 3, rank 2, rank 1. Okay, like this, because in that movie you can see this is how they were arranged. Okay, this is how they were arranged. The poor people were here and rich people were here. So anyway, a rank was given basically based on their money status. Now, so this type of relations are called order relation, in which we can put elements in some order. Now let's see the formal definition. You can see all these examples. All these are examples of order relation. For example, you can see this 42 is less than equal to 137. You can see, yes. So basically in the order this 42 will come first, then the 137 will come. But remember, 137 is not less than 42. So you can see there is a ordering here. Means 42 is less, 137 is more. Okay, so there is a fixed ordering here. You can't put like this, because 137 is not less than equal to 42. This is what I want to say. Basically in ordering, what we mean means, if this person A is related to this person B, okay, then basically this should not happen. Okay. Now we will see the formal definition. So if anyone has any doubt right now, then don't worry, because this was just an intuition. If you got it, then that's okay. If you did not get it, then there is nothing to worry, because now we will see the formal definition, and questions we will solve using that formal definition only. Okay, so if you did not get it so far, no problem. Okay, let's see the formal definition now. What is partial order relation? This is again a special type of relation. Remember, this is again a special type of relation, just like equivalence relation, just like reflexive relation, transitive relation, just like them. This is a special type of relation, and this is the relation which is reflexive, anti-symmetric, and transitive. These properties must hold. You can see in equivalence relation, if you remember the equivalence relation, in equivalence relation we have reflexive, we have symmetric, we have transitive. These three things we have in equivalence relation: reflexive, symmetric, transitive. But here in partial order relation we have reflexive, transitive is same. You can see reflexive, transitive both are same, but in equivalence relation we have symmetric. In partial order relation we have anti-symmetric. Okay, so this is our definition of partial order relation. Means a relation is partial order relation, R is partial order relation if R satisfy all these three properties: reflexive, antisymmetric, transitive. All these three properties must be satisfied: reflexive, antisymmetric, transitive. You should check all these three properties and you should verify whether they are satisfied or not. If all these three properties are satisfied, then you will say that R is partial order relation. Let's take example. Let's assume our base set is set of natural number. We are defining a relation R on set of natural number. Okay, basically a relation R we are defining on set of natural number, and that R, basically A is related to B. A is related to B if and only if A is less than equal to B. Tell me, this relation R, is this partial order relation? POR means partial order relation. Is this partial order relation? Tell me. Check reflexive, antisymmetric, transitive. These three properties you need to check. Let's see. This relation is partial order relation. Yes. Let's first check reflexive. First we will check reflexive. Yes, it is reflexive. Why? Because every element is less than equal to x. X is less than equal to x. For example, 3 is less than equal to 3. 3 is less than equal to 3. 4 is less than equal to 4. So every element is less than equal to itself. So this is reflexive. Means basically everyone has reflection. The second we should check is anti-symmetric property. What is anti-symmetric? We have already seen in yesterday's last class. What is anti-symmetric? Anti-symmetric says that between different elements there should be no symmetry. Take two different elements. For example, maybe 3, 4 you take. If you take 3, 4, then you will see that there is no symmetry, because this is true but this is not true. This is not true. So you can see between different elements there is no symmetry. Means if you have two different elements, let's assume you have A, you have B. Let's assume A and B are different. Then if A and B are different, then you know that only this can happen. Remember, only this can happen. This cannot happen between different elements. Both these things cannot happen. Exactly one of these things will happen. Okay, so you can say this is anti-symmetric because there is no symmetry between different elements. Okay, so you can see. Now the third property that we need to check is transitive. This is transitive also. Why? We have already seen that this is transitive in last lecture. You can refer there. This relation we have already seen in the last lecture, and there we have proven that this relation is transitive. How did we prove it? We assumed that A is related to B and B is related to C. This is we assumed. Now this means that A is less than equal to B. This means that B is less than equal to C. Now A is less than equal to B, B is less than equal to C. What it means? It means A is less than equal to B, less than equal to C. It means A is less than equal to C. And A is less than equal to C means A is related to C. A is related to C. This is what we want in transitive relation. In transitive relation, what we want? We want that if A is related to B, B is related to C, then A should be related to C. You can see A is related to C. So this you have proven that this is transitive. So this is reflexive, anti-symmetric and transitive. So this relation is a partial order relation. Now you see, again, let's check this same relation. Let's check this same relation. This same relation, let's check once. Okay, we have seen that this is partial order relation. We have seen this thing. We have seen this thing, that this is partial order relation. But now what this partial order relation is doing, like from where this order is coming, order. I told you every partial order relation, what it does, it makes some order. It puts elements in a order. Okay, it will put elements in a order. So how it is putting, you can see this relation A less than equal to B. This is how it is putting. It is putting like this: 1 is less than equal to 2, 2 is less than equal to 3, 3 is less than equal to 4, 4 is less than equal to 5, and so on. This is how this relation is putting elements in the order. You can see this element, this order you will get, right? Am I right? You can see this order you will get. So this relation we have seen that this is partial order relation. This partial order relation is putting elements of our base set. You can see all these elements are put in the order. You can see there is a ordering here, there is a ordering here. Okay, so this is how we can say that there is a ordering here. Basically the elements have been put in ordering. Now let's take one informal example. Let's take our Titanic example. Yesterday I told you that Titanic movie example was equivalence relation, and today I am telling you that Titanic movie example is partial order relation. Now you might be confused. How can same relation be like how can both like because you see equivalence relation means reflexive, symmetric and transitive. This is our equivalence relation. Partial order relation means reflexive, anti-symmetric and transitive. So reflexive, transitive, these properties are same, but equivalence relation says that it must be symmetric, and the partial order relation says that it must be anti-symmetric. So there is some difference between equivalence relation and there is some difference between partial order relation. Here we check symmetric property, here we check anti-symmetric property. Now we can take this Titanic example again, but now on this Titanic movie, basically this is our base set. Our set is set of all people on the Titanic. Okay, set of all people on the Titanic, or you can say basically set of all people on Titanic. Now this is our base set. Okay, this is our base set. Now we are defining a relation. Remember, I am defining two different relations. The first relation I am defining is this. The relation R1 I am defining. This is the relation R1 that I am defining. A is related to B if and only if A comma B have same money status. Same money status. Basically, let's assume that there are three money status: poor, middle class, rich. Let's assume, of course, in real life there are many different money status. Okay, even in middle class people also rich, middle class and poor. Now this is the relation we have defined. A R1 B means A is related to B if and only if A and B have same money status. Tell me, is this equivalence relation? Is this equivalence relation? Tell me, is this equivalence relation? Yes, Devika, let me see doubt. You can try this question. Let me see the doubt. So Devika is asking, what is direct proof, trivial proof, vacuous proof, indirect proof? So Devika, there are many proof techniques are there. Okay, many proof techniques are there. Okay, and proof techniques are in the syllabus, but the question cannot be in NET exam. They are not going to ask question like what is vacuous proof, what is direct proof, all these things. But I will give you some idea, don't worry, I will give you some idea. Okay, right now we are not studying this topic. Right now we are studying relations, partial order relation. That's why I am not taking this question. Okay, so either at the end of this class I can take your doubt, okay, or we can take your doubt in the next class, because this class is devoted to partial order relation. Okay, so Devika, you can just send me your doubt, or you can let me know your doubt in the next class. In the beginning of the next class you can let me know, and I will explain it. Okay, let me see if anyone has any other doubt. So there is, I can see Devika has a doubt, Amandeep has a doubt. X equal to x plus 1 will be an order relation. We will check it, Amandeep, we will check it. We will take your relation and then we will check whether that is a order relation or not. Let's see whether this is equivalence relation or not. Okay, let's come back to our question. So so this is reflexive, this is equivalence relation. Yes, why? First of all, this is reflexive, because same, of course, if you have a comma a, then of course a is having same money status as a. Both have same money status because both are same people. Of course, I have same money status as myself. Okay, so you can see this is reflexive. Yes. The second is symmetric. Yes, it is symmetric. Why? Because if a is related to b, let's assume that a is related to b, then what it means? It means a and b have same money status. Maybe both a and b are poor, maybe both are middle class, or maybe both are rich. Okay, so basically if a is related to b, then what it means? It means both have same money status. So b also related to a, because both have same money status, so b will also be related to a. So this is symmetric. Next, it is transitive. Yes, it is transitive. Why? Let's assume that a is related to b. Also, let's assume that b is related to c. Now, if a is related to b, what it means? It means a and b have same money status. If b is related to c, what it means? It means b and c have same money status. Maybe, for example, maybe a and b both are both are rich. Let's assume both are rich because they have same money status. So let's assume they both are rich. Then because b is rich, so now c is automatically rich because b and c also have same money status. So b comma c both are rich. A is rich, b is rich, c is rich. Then we can say that a is also related to c. Why? Because a and c are rich, so they have same money status. So you can see this relation is equivalence relation. Remember, this relation is equivalence relation. If you see this relation R1, this is not partial order relation. Check for fourth property, you check anti-symmetric. Tell me, is it anti-symmetric? Tell me, is this relation R1, is it anti-symmetric? Marathi, is this quasi ordering in the syllabus? I don't think it is in the syllabus. Have you seen any question in the previous net exam? If you have seen, then you let me know. Have you seen any question from quasi ordering in the previous net exam? Array, this is not anti-symmetric. This relation R1 is not anti-symmetric. This is not anti-symmetric. Why? You see, let's assume we have two different people we have. Let's assume both are poor. Okay, both are poor. You can see. Okay, maybe this our hero Jack. Okay, and maybe his friend, Jack's friend. Okay, so his friend, basically his friend. Okay. Now you can see that both are different people, both are different elements. Now you can see Jack is related to his friend. Why? Because both have same money status. So you can say that Jack is related to his friend. But his friend is also related to Jack because both have same money status. So you can see this R1 is not an anti-symmetric relation. Anti-symmetric says that what anti-symmetric says? Anti-symmetric says that between different elements you should not have You should not have symmetry. Basically, if A and B are different, let's assume A is related to B, then B should not be related to A. This is not anti-symmetric. Is this clear? Many students have said that this is anti-symmetric. This is not anti-symmetric. Is this thing clear? Is this doubt clear? Yes, different people can have same money status. Of course, different people can have same money status. So basically, this Jack is related to his friend, and this friend is related to Jack. So different between different elements there is a symmetry. So we can say that this is not anti-symmetric. So this is not anti-symmetric. Now because this is not anti-symmetric, so we can say that this is not partial order relation. This is not partial order. This R1 is not partial order relation. So this R1 is a equivalence relation. What it does? This equivalence relation, what it does? And you already know all these things, that every equivalence relation what will do? Every equivalence relation will partition our base set. What is our base set? Base set is people on this Titanic. Base set is people on this Titanic. Okay, this is our Titanic, this is water. So people on this Titanic is our base set. And if every equivalence relation, I have already told you this thing in the last lecture, that equivalence relation partitions our base set. It will partition our base set. You can see this equivalence relation R1, it will also partition our base set. With the one set will be rich, another will be middle class, and another will be poor, middle class. Another will be poor. So you can see there is a partition. This relation R1 is basically partitioning our base set, means set of people on the Titanic. That set of people has been partitioned into three classes. This is class, this is class, this is class. You can see every two person in this class are related. Why? Because they have same money status. Every two person in this class also are related. Why? Because they have same money status. You can see that if one person is here, Jack is here, Rose is here, you can see they do not relate to each other. Why? Because they do not have same money status. Basically this relation R1 partitions our base set, because this relation R1 is equivalence relation. Every equivalence relation will partition our base set. Okay, so this is how in three classes this relation R1 has partitioned, has divided our base set. Okay, now on the same set of people, I am giving you another relation R2. Now I am giving you another. So okay, on this same set S, on this same basically set of people on the Titanic, on this same set S, now I am giving you another relation R2. A is related to B, if and only if A is A basically the money status of A is less than equal to money status of B. This is what I want to say. Money status of A is less than equal to money status of B. Remember, this and this are different. This is R1 relation and this is R2 relation. Both are different. You will see. You check it out. Both are different. This R2 relation is saying that A is related to B if and only if money status of A is less than equal to money status of B. Tell me, is it what it is? Like, is it partial order relation? Is it equivalence relation? What it is? Tell me what it is. This R2. You need to tell me R2. What it is? Partial order relation, equivalence relation, what it is? So you can see this is partial order relation. Why? First of all, this is a reflexive. First of all, why? Because of course I have my money status is less than equal to my money status. Every person has money status less than equal to himself, herself, whatever. Next, anti-symmetric. Yes, it is anti-symmetric, because if you have two different people, wait a second, okay, this is not anti-symmetric. Wait a second. Okay, this is not anti-symmetric. Okay, so this is not anti-symmetric, this is not anti-symmetric. Wait a second. Yeah, okay. Because here we have done three. Here we have three money status: rich, middle class, poor. Three money status we have here. Okay, total three money status we have here, and of course, if this Jack you can take, this Jack is less than equal to his friend, because both have basically same money status. Now his friend is also less than equal to Jack, because both have same money status. So Jack is less than equal to his friend. Basically money status of Jack is less than equal to his friend. Also we can say that this friend has money status less than equal to money status of Jack. So this is not anti-symmetric. This is not anti-symmetric. Okay. So yes, this is not anti-symmetric. Okay, this relation is also not anti-symmetric. Yeah, okay, so let's leave this example. I was thinking something else, but anyway, you can see this is not anti-symmetric. The reason this is not anti-symmetric is this, that because I told you we have three money status: poor, middle class, rich. Three money status we have. Now you can see that this Jack, the money status of Jack is less than equal to his friend. You can see the money status of Jack is less than equal to his friend. Okay, now the money status of this friend is also less than equal to Jack. This money status of this friend is also less than equal to Jack. So that's why basically this is not anti-symmetric, because there is symmetry between different people. Okay, actually this is symmetric. So this relation is actually symmetric, and so this relation is symmetric, you can see, because yes, sorry, this is not symmetric. This is not anti-symmetric, this is not symmetric. Okay, so anyway, leave this example. Actually this is not anti-symmetric, I told you, because between different people there is symmetry. Okay, similarly actually this is not symmetric also. Why? Because you can see the money status of Jack is less than money status of Rose. Okay, yes, true, but money status of Rose is not less than equal to Jack. So basically symmetric property is also violated, anti-symmetric property is also violated. So this relation is neither symmetric nor anti-symmetric. Okay, are you getting my point? So is this point clear? Because money status of Jack is less than equal to money status of Rose, but money status of Rose is not less than equal to money status of Jack. So this is how you can see. Anyway, okay, let's leave out. So we were looking at partial order relation. Let's take one numerical example. Let's take one question, and in this question what we will take, let's take set of subsets of A. Let's assume A is 1, 2, 3. Let's assume this is our set A. Our base set, remember our base set is not A. Our base set I am taking PA. What is PA? PA means power set of A. Power set of A. You already know what is power set of A. Power set of A means collection of subsets of A. Means, for example, 5 will be here, 1 will be here, 2 will be here, 3 will be here. For example, 1, 2 will be here. Okay, 1, 3 will be here, 2, 3 will be here, 1, 2, 3 will be here. You can see. So see, this is our set A, but our base set, remember our base set, we will define relation on this base set. We will not define relation on A. We will define relation on this base set PA. PA means power set of A. You already know what is power set of A. Power set of A means collection of subsets of A. So this is subset of A, this is subset of A, this is subset of A, and so on. So if you take the collection of subsets of A, then you will get power set of A. So this is our power set of A. Now on this power set of A, we are defining a relation R on PA. On this, basically this relation will consider these elements. Remember, these elements will be considered. Okay, always remember this thing. first of all you need to check on which set we are defining our relation. This is important. For example, here we have two sets. One set is A, another set is power set of A. I am telling you that we are defining our relation on power set of A, means on this set we are defining our relation. We are not defining our relation on this set. Now when we are defining relation on this set, then these are the elements which will be related to each other. These are the elements which will be related to each other. Okay, now so we are defining a relation R on power set of A, and what is the rule? The rule is this. A is related to B, means one element is related to another element if and only if A is subset of B. A is subset of B. Remember, this is subset. A is subset of B. This is our relation. Okay, this is our relation. Basically, we are defining a relation R on power set of A. A is related to B if and only if A is subset of B. Now, first thing you need to tell me, is it reflexive? This is my first question. Is it reflexive? Yes, Amandeep, there in that example we should have more information. I was trying to make a analogy, but I will check. I will think about it. Maybe I can make some nice analogy. But anyway, you take this example. You take this. This is our numerical example. We can see. Actually, these analogies that I am giving, these type of questions are asked in TIFR exam. There is this exam, TIFR. This exam is there. This exam has high level than GATE exam. Even GATE exam is also easy than TIFR. So this TIFR exam is there. In this exam, you will notice one thing, that they mostly ask questions. Many times they ask questions by making a scenario. They will make a scenario, like they will make a set of buildings. They will basically give you a city. They will tell you that in this city we have building, we have road. So they can also define this Titanic scenario. Basically, in this exam, TIFR exam, the questions are like this. They make some scenario, they make a complete scenario. They will complete detail will be given to you. Almost 6 or 7 lines of paragraph will be given to you, just to describe the situation, just to describe the analogy. Then they ask questions based on that analogy. So these type of questions are asked in TIFR exam, and I like those questions. That's why I try to come up with such type of analogy. But anyway, nothing to worry. Let's see this example. Is this reflexive? So yes, this is reflexive. This is reflexive. I told you already what we mean by reflexive. Reflexive means a set is subset of itself. Yes, a set is subset of itself. Remember, just because I am writing small a, that does not mean that this small a is some element, is some element. This is a set. That's why I was repeating again and again that this relation R is on set PA. Means on this set we are defining this relation R. In this set we have elements. These are the elements that we have in this set. All these elements are themselves set. You can see all these elements. Just look at each element. Each element itself is a set. Okay. Now we are saying that a set A is related to set B. Set A. Remember, this A means set. Why? Because this A is element of PA. Element of PA itself is a set. So this set A is related to set B if and only if A is subset of B. Now we are asking, is it reflexive? Yes, it is reflexive. Why? Yesterday I told you that every set is a subset of itself. For example, this set is a subset of itself. Every set is subset of itself. So this is reflexive. For example, phi is subset of phi. because yesterday I told you that every set is a subset of itself. The second thing, that is, let's check for symmetry. Let's check for symmetry. Is it symmetric? Let's check for symmetry. So Exot is saying that we should take TIFR question. The reason we are not taking TIFR question is that this TIFR, you can put them in order. Like this TIFR level is greater than the like harder than the level of gate, and the level of gate is harder than the level of net. So you can see right now we are studying for net exam. Right now we are studying this crash course for net exam. So if we take questions from TIFR exam, then that will be not beneficial. Okay, this TIFR has a like different level. This TIFR exam has a complete different level. This net exam and this between this net exam and TIFR exam there is another level, that is gate level. Okay, so that's why we are not taking questions from TIFR. I am not taking questions from TIFR. I am just saying that in TIFR question they make creative questions. This is like a nice thing about this exam. Every question is creative, every question is new, every question is creative. Okay, in gate exam also some questions are creative, some questions are new, not all. For example, 65 questions are there. Out of these 65 questions, almost 30 questions are creative. Remaining 35 questions are not creative, you can say easy questions. But 30 questions are creative. In TIFR exam, every single question is creative. Okay, in net exam basically mostly new questions they do not ask. They just repeat almost those same concepts. They will keep on repeating. So that is in net exam basically the concepts. If you solve all the net questions, if you solve all the previous net questions, then you can very easily you can crack net exam. You can even crack JRF also. Okay, because in net exam what they do, they basically just modify the data. They just basically change the data and they repeat the question. So this type of thing happens in net exam. That's why previous year questions are important. You should solve all the previous year questions of net exam. Once you solve all the previous net questions, you can guarantee that you will qualify net exam. You might also qualify JRF also. Anyway, let's see whether it is symmetric or not. It is not symmetric. It is not symmetric. Why? See, this is subset of this. You can see. So this is subset of this. Symmetric says that if this is subset of this, then this also should be subset of this. But this is not happening. Are you getting my point? You see, it is not symmetric. Why? Because you can see this set is subset of this set. For example, this element, you just look at this element. This element is related to this element. Why? Because this set is subset of this set. But this set is not subset of this. So symmetry property is violated. Are you getting my point? Symmetry property is violated. You can see that this element is related to this element. Okay, this element is related to this element, but this element is not related to this. Wait a second, I think earthquake is coming. I felt like some earthquake came. Suddenly my table was like vibrating. Anyway, so let's see this. So what I am saying, are you getting my point? So let me take a new slide. See, you see our base set is this. Our base set is this. This is our base set. in our base set we have subsets. You can see in our base set we have these subsets are basically the subsets of A. The subsets of A we have in our base set. This is our this is set A, but this is our base set. Okay, basically we have subsets of A. Okay, subsets of A will be there, I told you. Now let's check for symmetric property. It is not symmetric. Why? Because for example you can see this phi is a subset of this. Means this element is related to this element. Symmetric property says that this element should also be related to this element, but it is not happening. You can see this is not a subset of phi, so that's why this is not symmetric. No, I just felt it. I am not saying that earthquake came. I am just saying that I felt it. Then I went to my mom and I asked her, and she is saying that nothing happened. Okay. Okay. So anyway, some fake feeling maybe. Anyway, so this is not symmetric. Okay. Focus on this. Okay, focus on this. Focus on the question. Don't focus on other things. I am feeling completely well. Just focus on this question. Don't distract. Focus on this question. So this is not symmetric. Let's check it. Is it anti-symmetric? Tell me, is it anti-symmetric? Actually 2 months back the earthquake came in my district. I am from this district, Zunzunu. So in my district 2 months back this earthquake came, and the intensity was I think 4.7. This was the intensity. Okay, so this was the first time like in the last 50-60 years this happened for the first time that in my city this earthquake came. Okay, before that I asked my grandfather. He also told me that he has not experienced any earthquake in whole life in my district, but 2 months back 4.7 intensity earthquake came. So nowadays anything happens, anything slightly happens, and we just we just think that this is earthquake. Anyway, so let's see, is this anti-symmetric? Yes, this is anti-symmetric, because if you take two different elements, then you will see that there is no symmetry. For example, you can see this phi is subset of this phi is subset of this, but you can see this is not a subset of phi. So you can see between different elements there is no symmetry. Or you can check like this. Don't worry, you can check like this. Let's assume that there is symmetry. Let's assume that S1 is a subset of S2. Let's assume S1 is subset of S2. S2 is subset of S1. Let's assume that S1 is subset of S2 and S2 is subset of S1. Basically, let's assume that there is symmetry. So yesterday I told you that in anti-symmetric what happens? In anti-symmetric it happens that if A is related to B and B is related to A, if both these things happen, then if both these things happen, then what should happen? Then A should be equal to B. I told you this yesterday in anti-symmetric property. I told you that if this and this happens, means if there is symmetry between two elements, then they should be same element. Basically they should not be different element, because I am saying that in anti-symmetric property between different elements there should be no symmetry. Okay, between different elements there should be no symmetry, means if there is symmetry then both elements should be same. Now let's assume that there is symmetry. S1 is subset of S2 also let's assume that S2 is subset of S1. Let's assume both these things. Okay, let's assume both these things. See, if S1 is subset of S2, S2 is subset of S1, then what will happen? Then S1 is equal to S2. Okay, so remember, if S1 is subset of S2 and S2 is subset of S1, then what will mean? It will mean that S1 is equal to S2. So that's why this is anti-symmetric. This is transitive. You can check this is transitive because you can see that if this S1 is subset of S2 and S2 is subset of S3, then it will mean that S1 is subset of S3. So this is transitive also. Okay, this is transitive also. Are you getting my point? I am saying that if S1 is subset of S2, S2 is subset of S3, then S1 is also subset of S3. So this is transitive also. Okay. Okay, so Pratibha is asking, if R is equivalent, then R is not POR. No, this is not true. You can see, for example, you consider this relation. Okay, Pratibha, consider this relation. Let's assume this is your set A, and we are defining a relation on set A like this: 1, 2, 3, 1, 2, 3, and we are defining this relation. Let's assume this relation we are defining. Okay, now this relation R, if you check, this is reflexive. You can check this is reflexive. Why? Because every element is related to itself. 1 is related to 1, 2 is related to 2, 3 is related to 3. So it is reflexive. You can check this is symmetric. We have already taken this example in last class. You can check that this is symmetric. Okay. Also this is transitive. Also you can check this is transitive. In last class we have already taken this example. That's why I am just directly writing. You can refer to the last lecture. There I have explained why this is symmetric, why this is transitive. Everything I have already explained. So that's why I am directly writing that this is symmetric, this is transitive. We have already seen this thing. This is anti-symmetric also. This is anti-symmetric also. So you can see all these properties are satisfied. Now if you see, because of this reflexive, symmetric, transitive, because of these three properties, we can say that R is equivalence relation. R is equivalence relation. And because of these three properties, because of these reflexive, transitive, anti-symmetric, because of these three properties, we can say that this is partial order relation also. So this relation R, this is equivalence relation, also this is partial order relation. This is both. So Pratibha, is your doubt clear now? That a relation can be both equivalence relation and partial order relation. Okay, this relation. So basically, if a relation is equivalence relation, then that does not mean that that is not a partial order relation. Okay, is this doubt clear? See, Prerna, this property we have, S1, set S1 is equal to set S2, set S1 is set equal to S2. What it means? It means S1 is subset of S2 and S2 is subset of S1. Okay, basically S1 equal to S2 if and only if S1 is subset of S2 and S2 is subset of S1. So basically whenever these two things happen, whenever S1 is subset of S2 and S2 is subset of S1, whenever this happens, then we can say that S1 is equal to S2. Okay, this is what I used. So I basically proved that using this, I proved that this is anti-symmetric. Our relation was anti-symmetric. This is how I proved it. Okay, basically remember, if these two things happen, then this will happen. This is what I showed. I did not tell you, I did not say that S1 is subset of S2, then S2 is subset of S1. This is not what I said. I said if these two things happen, then S1 is equal to S2. This is what I said. Okay, you are misinterpreting my statement. Okay, I did not say that if S1 is subset of S2, then S2 is subset of S1. This is not what I said. Okay, are you getting my point? I said that if both these things happen, then S1 is equal to S2. This is what I said. So okay, this is our partial order relation, and we have seen few things, and we can see one is something called total order relation. We have something called total order relation. What is total order relation? Total order relation means a partial order relation. First of all, it must be a partial order relation. Okay, first of all, it must be a partial order relation, and then first, okay, this is the first condition. So partial order relation, and every element should be related to every other element. Basically we can say that if you take any two elements a comma b, you take any two elements a comma b, okay, whatever you want to take, you take any two elements a comma b, then basically they must be related. Means a should be related to b. This is what we want to say. Total order means first of all it must be a partial order. So first of all you need to check partial order. First you need to check reflexive, anti-symmetric, transitive. Then once it is partial order, then you can check that for every two elements, okay, basically every two elements a comma b you take, then a should be related to b. This is what we mean by partial order relation. Let's take example. Let's consider this n is our base set, and we are defining a relation R on n such that a is related to b if and only if a is less than equal to b. Consider this. Okay, this we have already seen. This same relation we have already seen that this is partial order relation. In today's class we have seen that this relation we have already taken in today's class, and we have seen that this is partial order relation. So okay, yes, it is partial order relation, but I told you total order relation means first of all it must be a partial order relation, and for every two elements they must be related. Means you take any two elements. For example, you take 10 and 20, you can say 10 is less than equal to 20. So you take any two elements you can take, and you will see that they are related. For example, you can take 3, you can take 2, then you will see that they are related because basically this 2 is less than equal to 3, so you can say that 2 is related to 3. You can see like this. So whatever two elements you take, you will see that they are related. Okay, so this is what we mean by total order. Total order means first of all it must be partial order. Okay, then once it is partial order, then partial order relation, and every two elements must be related. Every two elements, whatever two elements you take, they must be related. Okay, so then we will call it total order relation. Okay, you can see this total order relation. Why we call it total order? Because this total order relation will put all the elements in a chain. For example, this 1 is less than equal to 2, 2 is less than equal to 3, 3 is less than equal to 4, 4 is less than equal to 5, and so on. You can see there is a chain here. So sometimes this total order relation is also called chain. Total order relation, sometimes this is also called chain. Okay, either you can call it chain or you can call it total order relation. What it means, chain, total order relation, both are same thing, synonyms. These are synonyms of each other. And what it means that first of all it must be a partial order relation, and for every two elements a comma b, they must be related. So this is our partial order relation definition. For example, you can check this same thing. You can take this example. This was our set A, and this was our base set, power set of A. If you remember, this example we have already taken. So in this example you can see we have proven that this we defined a relation. Like this: A is subset of B. This was our relation. If you remember, this was our relation. A is subset of B. Now we have already proven that this relation is reflexive, this relation is symmetric, this relation is transitive, anti-symmetric. We have already proven that this is reflexive, anti-symmetric, transitive. All these things we have already proven. So basically this relation R is a partial order relation. Okay, this relation R is partial order relation. And now once it is partial order relation, now we need to check basically whether every two elements are related or not. No, every two elements are not related. For example, you take this element and you take this element. You can see that this element is not related to this. Also, this element is not related to this. You can see why? Because you can see this is not a subset of this. Similarly, this is not a subset of this. So you can see that this element and this element, they are not related. So we can say that this is not a total order relation. I told you total order relation means partial order and every two elements must be related. But here you can see that these two elements are not related to each other. Neither this is related to this or nor this is related to this. So that's why this is not a total order relation. Okay, so this is our partial order relation and total order relation. One last thing is remaining, but let me check if anyone has any doubt. If your doubt has not been resolved yet, then you can just right now you can ask again. I am looking at the comment box. I'll answer your doubt. Prerna is asking, sir, symmetric set is equivalent always. Prerna, there is no such thing as symmetric set. Symmetric set, there is no such thing. You can see this symmetric set. There is no such thing as symmetric set. We have not used this word. Symmetric relation is there. Symmetric relation is there. Symmetric relation is there. Symmetric set, there is no such thing as symmetric set. Okay, this terminology, this term is not there. Okay, now we have symmetric relation. So if your doubt is that every symmetric relation is equivalent, then this is not true, because equivalence relation means reflexive, symmetric and transitive. All these three properties must satisfy. Just by symmetric property, just by symmetric relation, you cannot say that this is equivalence relation. All these three properties must satisfy. Okay, yes, Sukhpreet, every element must be comparable to every element in the set. For example, we saw when we took this example x less than equal to y, when we took this example, in this example you can see that every element is comparable, or you can see related. Every element is related. Okay, remember, total order relation. Total order relation means partial order relation plus every two elements must be related. I told you this. For example, in this relation x less than equal to y, in this relation you can see that you take any two elements. For example, you take 5, you take 7. You will see that 5 is less than 7, means 5 is related to 7. Okay, so remember, whenever you are checking for total order relation, then first you need to check whether it is partial order relation or not. So partial order relation plus every two elements must be related. Means if you have two different elements a, b, then you should have a is related to b. You should have this. But if you remember our example, this subset example that we took, x is subset of y. This subset example we took. In this subset example, you can check that this is not related to this. Neither this is related to this, nor this is related to this. Basically, this and these two elements are not related, you can see. Okay, so you can see that's why this is not a total order relation. Sukhpreet, is this clear? Very easy, just first check partial order relation, then check that, and every two element they must be related. Every two element a comma b you take, then a must be related to b. Okay, so if anyone has any other doubt, then you can ask. So let's see the last thing. Today we will see this last thing. Every partial order relation, if you see, every partial order relation if you see, then that partial order relation actually can be represented by something called hash diagram. This is a special thing, hash diagram. Okay, this is a special thing, hash diagram, special. Now if you have any partial order relation, then you can represent it with hash diagram. You see, every partial order relation is reflexive, every partial order relation is anti-symmetric, and every partial order relation is transitive. All these properties are satisfied by partial order relation. Okay, now what you do, for example, let's consider this. Let's assume you have this set A 1 2 3. Let's assume this is your set A 1 2 3, and on this set A we are defining a relation that is less than equal to, for example, A is less than equal to B. This is the relation that we are defining, A is less than equal to B. This is the relation that we have defined. You can check that this relation is reflexive, this relation is anti-symmetric, this relation is transitive. So this relation A less than equal to B, this relation is partial order relation. I am saying that every partial order relation has a special diagram, that is hash diagram. Okay, what is this hash diagram? Hash diagram is nothing but, I told you, a ranking system. Basically you arrange elements in ranking order. So that's what I mean. Basically first you put 1, why, because you can see 1 is less than equal to 2, 2 is less than equal to 3. So this basically this is the order, so you can put 1 on the bottom level, then you can put 2, then you can put 3. Why? Because 1 is related to 2, this 2 is related to 3. So this is the hash diagram. So in hash diagram what we do like this. If A is there, let's assume A is there, B is there, let's assume they are related, then you will put them like this. Because if A is related to B, then what will mean in partial order relation, whenever A is related to B, then what it means? It means that A is related to B, and because of anti-symmetric, because this partial order relation is anti-symmetric, because of this anti-symmetric property, we can say that B is not related to A. So you see, because of this anti-symmetric property, there is a ordering here. Okay, so that's why whenever we have A is related to B, then we will put them like this. A will be on the bottom level, B will be on the top level. This is how we will put them. Okay, so this is our hash diagram. Let's take one more example. Let's take this example. Let's assume this is our set A. The set A is, let's assume, you can take 1 2 3 4 6 12. Let's take this. This is our set A. Now we are defining a relation that is divide relation. Means A is related to B if and only if A divides B. This is our relation. Let's assume this is our relation. Okay, A is related to B if and only if A divides B. Devika, we will cover PYQ questions. Let's do one thing. Tomorrow we will cover the PYQ questions of mathematical logic. Okay, tomorrow we will cover it, because I told you that I want to utilize those 3 classes in the schedule. If you see in the schedule for graph theory, we have 3 classes for graph theory. These 3 classes are there. So I have already sent you the link of graph theory. 3 links I have sent you. You can watch those 3 links, because I taught graph theory almost 1 or 2 weeks ago. I taught graph theory. So those 3 links I have already sent you. And in the schedule, the 3 classes for graph theory, I want to utilize them to solve more questions. So let's do one thing. Tomorrow we will solve previous year questions of mathematical logic, propositional logic, first order logic. So we will solve these questions. So you should attempt it. Okay, because if you do not attempt, then these classes, these solution sessions will not be beneficial. So you must attempt them. Okay, before coming to the class, you must attempt it. So today you have time. You can attempt the previous year NET questions. Remember, only NET questions. The previous year NET questions of mathematical logic you can attempt today, and tomorrow we will discuss. For 2 hours we will discuss many questions, we will discuss, and I will take those questions in which you have doubt. So okay, so you can do one thing. You can let me know in which questions you have doubt, and I will take those questions in the tomorrow's session. We will discuss how to see this. Anyway, I will not cover optimization. Optimization will not be covered by me. It will be covered by, I think, Abdul sir will cover. Okay, let's do one thing. Let's solve this last question, and then we will conclude our session. Focus on this question because operating system class is about to start. So focus on this question. This is our set A, 1, 2, 3, 4, 6, 12. This is our set A, and this is the relation we have defined. A is related to B if and only if A divides B. A divides B. You can check. Okay, you can check after this lecture is over. Then you can check tonight. You can check that this is partial order relation. You can check because this is reflexive, this is anti-symmetric, and this is a transitive. All these three properties are satisfied. You can check. But I am going to tell you how to draw the hash diagram because this is partial order relation, and I told you every partial order relation has a special diagram, hash diagram. How to draw that diagram? So that diagram you will draw like this. See, the 1 will come in the bottom. Why? Because basically 1 is related to everyone. 1 divides everyone. Okay, 1 divides everyone. 1 divides 1, 1 divides 2, 1 divides 3, everyone. So 1 will come in the bottom because 1 is related to everyone. I told you, whenever A is related to B, then how do we put it? We put it like this. Whenever A is related to B, then we put it like this, A, and then at the upper level we put B. Similarly, this 1 is related to everyone, so we put 1 in the bottom level. Then we, on the next level, because this 1 is related to 2, so we put this 2 on the next level.